So here in this video we're going to look at a couple plots and also just sort of go through the process of like how would you actually do this in practice to determine activity coefficients for your solvent and solute. So this is an example for sucrose. This is a sucrose solution in water, and we're looking at the mole fraction of water here on the x-axis here. So over here on the left we have pure water, and this has a specific value of the vapor pressure. So this is our P2 star, or sorry, P1 star, because 1 is always our solvent here. And the line here on the top, this is the Raoult's law behavior. So this is our linear behavior. And the line on the bottom is experimental data. So what we can see is that very dilute solutions up to, I don't know, about here or so, we can see that we get a decrease in vapor pressure as we predict from Raoult's law, and it follows that linear trend. Based on the mole fraction. So as the mole fraction decreases, the vapor pressure decreases because there's some other stuff present in the solution that prevents some of the water from evaporating. But once we get past that, dilute solution about 0.97 or something, we start to see deviations here, right? So we see this deviation between the experiment and the Raoult's law ideal behavior, right? This is our ideal. And this is this is what the osmotic coefficient is sort of allowing us to correct for us to see that. And this is a consequence of the fact that that we have non-ideal behavior in these solutions, that this doesn't just strictly follow Raoult's law, that these interactions between our solute and our solvent are not the same as between the solvent and solvent or the solute and solute. And so we can use data like this to be able to find the osmotic coefficient as a function of molality. And so this, if we were behaving ideally, this would just be a flat line right at 1, right? It would look like this. But this osmotic coefficient tells us how this is not behaving ideally. And we see as the molality increases, we see an increase in the value of phi. Now, how would we actually use this to calculate activity coefficients and activities so that we can use those in, say, equilibrium calculations or whatever? So we have our data here, and similar to what we've seen in a few spots here, if we have this empirical data, we can fit it to a polynomial. So fit to some sort of function, polynomial makes sense. This is similar to what you would do maybe for fugacity coefficients as well. And that gives you a function that describes phi. And then you can, once you have that fit, you can plug it into our integral so we had this equation that we looked at in the last video where we can just find these values, right? We measure phi, so we can get that from either our fit or just the measured values, and then we can do this integral here up to whatever value of molality we're interested in of phi minus 1 over m dm. Right, so we have, technically we should have primes on them. So, we're not integrating this curve directly, but we're integrating a variation of this, right? If we took phi minus 1 divided by m prime. So you could either fit this curve, or you could fit this function here if you calculate that, similar to what we did for fugacities. So sort of a step-by-step, how do we find the activity of the solute? From all these equations, let's just practically, how do you do this? 1, you would measure the vapor pressure as a function of concentration. And remember, P1 is the vapor pressure of our solvent. We can't really measure the vapor pressure of our solute, which is why we need to go to all this trouble. But what's happening to the solvent, it reflects what's happening with the solute, and that's why this works. Physically speaking, right? They're not independent of each other. So we measure P1 as a function of concentration. So that was the first plot that we looked at. Step 2, we can calculate the activity of the solvent, right? Using just the definition, using P1 over P1 star, and then we can compare, how does that compare, right? This log A1 is about equal to negative x2. We have this approximation from the Gibbs-Duhem relationship. From that, we can get phi versus concentration. So the deviations from this equation, which we have looked at in the last couple of videos, give us the values of the osmotic coefficient phi. So once we have phi versus concentration, step 3 is we can get the activity coefficients from the equation that is just up here, this equation over here. Get phi 2n by integrating that equation. All right, so it's a roundabout process, but that allows you to account for the non-ideal behavior. And once one person has measured this at a particular temperature, nobody else has to do it, right? We can all just use the values that they got. And so these are things, again, that you can look up in a table. And this particularly applies to non-electrolytes. When we talk about electrolytes, it's not as straightforward as this, and there are theoretical calculations that we can use to find activities that we'll talk about at the end of this chapter. But this sort of concludes for right now this section about activities and for non-electrolytes and how we find those using measurements of pressure.